All right. Okay, both ways. Attention up here, please. Okay, I'd like to get you through this, hopefully a little bit early, so if you have questions, I can answer a few questions. Pick up where we left off yesterday. Remember, we're talking about solving polynomial equations where we have to factor using those patterns we talked about yesterday. So first of all, let's just review the patterns, see if you remember the patterns.
Are you recording this?
I am recording. Thank you for asking. Okay, so you tell me real quick, without looking at your notes, see if you do this by memory. What's the pattern for something of the form a squared minus b squared? So we call that a difference of squares. Yes, sir?
A plus b times a minus b.
There we go. Okay. How about a sum of squares? What is it? It's just that. There's no pattern. Right. So there's no pattern. Right. What about something like a difference of cubes? So let's build this one think about how we build this one. Remember? Okay, we had a small linear pattern, big quadratic pattern. So what are the terms? A and B squared. Okay, now let's do the signs.
Opposite.
No. It's the same, opposite, plus, right? Okay. How about this one then? There you go. Okay, you got them all, right? No big deal. Okay, so what about something like that? I didn't give you that pattern.
You go back. X.
Yeah.
4, 3,
That's longer than 5 seconds.
2, 1.
Okay. All right. So I didn't give you a pattern for this, but we don't need one. How come?
It's just x squared.
Okay, because we can think of this as a difference of squares. If you break this up like x to the fourth, we could think of as a packet of x squared, right? So instead we'll rewrite that as right? I can think of that as being an a squared if a is x squared, right? What do I do with the 16?
Squared.
That's just a 4 squared, right? That's no big deal. Okay, so then we got, our first pattern is a difference of squares, right? So what's that give us?
X squared plus 4.
Either one, minus 4
Squared.
times,
X squared. Plus 4.
okay? We done?
No.
Because
You can simplify.
what pattern is that following?
Another.
Difference of squares,
Yeah.
right? That's x squared minus 2 squared. So that one's going to break up into x minus 2 times x plus 2. And then this one, we're just stuck with, right? Okay. So our goal here, now if it asked us to, I want to make a distinction here. This is completely factored. So on the first assignment, I'm going to ask you to do 2 different things, and I want you to make sure you understand what those 2 things are. One thing is I'm going to ask you to completely factor an expression. So I wouldn't have had an equation up here. I would have just had something like x to the 4th minus 16. If I tell you to completely factor it, that's completely factored because we ran out of patterns. right? There's nothing else to do, okay? If we're solving the equation, did we even need to take that step though? Not really, right? I mean, if we're just solving the equation, if we're setting this thing equal to 0, couldn't we have done that, kind of bailed off the factoring train right there? We didn't need to do that extra step. Because at this point right here, this is kind of, remember what our rules were at the end of the day yesterday, right? If we're taking some polynomial equation, and this is a polynomial, a 4th degree polynomial, isn't it? It's a binomial, but it's a 4th degree polynomial, right? With only 2 terms. We need to break that thing down far enough so that each of the individual factors is quadratic or smaller, right? So 2nd degree or smaller, which we did. We got them down to where I got, this is a product of 2 quadratic factors, right? Once they're quadratic factors, then it's just a matter of convenience whether I want to factor them or not, right? If it ends up being like later on, if it ends up being, not probably today, but I'm going to challenge you guys with some harder ones, where we might start off with a really big polynomial, and when we break it down into quadratic factors, maybe one of those quadratics is a trinomial that's easiest to solve by factoring, right? So then maybe you want to keep factoring. Like what if, for example, this factor right here, this first factor, instead of being x squared minus 4, what if it were something like x squared plus 7x plus 12 times some other factor? And I'm going to apply the 0 product property and set that equal to 0 and solve. How would you solve that one? Well, you'd factor it, wouldn't you? Right? Because you can find magic numbers. You see my point? But in this case right here, do we really need the magic numbers, or do we need to factor it? No, these are pretty easy equations to solve, aren't they? Right? If we just apply the 0 product property. So let's do that. By the 0 product property, we know that x squared minus 4 equals 0, or x squared plus 4 equals 0, right? Did you get that? So if we solve those 2 equations, those are pretty easy to solve. Let's take this first one. If we do, let's get rid of this. What are the 2 steps in order to isolate x there? Add 4 and square root, and what am I going to get? Plus or minus 2, right? Okay. So there's 2 solutions right there. Let's take the other equation. X squared plus 4 equals 0. The other equation that we got by the 0 product property. Same 2 steps, isn't it? Only I'm subtracting 4 this time. So I'm going to get x squared equals minus 4, so x equals plus or minus 2i, right? So we found our guaranteed 4 solutions, didn't we, right? How many solutions, complex solutions, do we know there are for this equation? 4. Have to be 4, right? Now, some of them could have multiplicities higher than 1, possibly, right? But in total, there has to be 4 by the fundamental theorem of algebra and its corollary. So we found them, though, right? If we listed them all out like in Moodle, the answer would have to look, the order doesn't matter, but it would have to look something like in the answer box. Something like that, right? I separated with commas. Okay? Make sense? Okay. If I was only looking for the real ones, I would know that I'm not getting any real ones from that factor and only have taken the plus or minus 2, right? Okay, so let's keep going. How about one like that? Nice. That looks pretty hard, right? X to the 4th, x squared. You see a trick though? And what should I probably do first?
Square root.
No. Okay, move the 2 over. I got to put it in standard form, don't I? Set equal to 0.
After you do that.
Okay. Okay. There we go. Right. So now what? I I can't isolate x, right? That's not an option, because I've got different x terms there. So what do you think? Any ideas?
Can you pull X out?
I can't, because there's no x in the 18. I can't square root the entire thing either, because it's going to be a mess. What does it do?
Sometimes you just gotta deal with mess.
This isn't a good mess.
Sometimes you just act as bad.
No, we never do that.
Divide by
Okay,
X.
now let me ask you this. Do you see a way where we could we regroup some things here so this looked more familiar? Wouldn't it be nice, wouldn't it be great if this looked instead, what if this looked like u squared minus 7u minus 18 equals 0? That's familiar, isn't it? I mean, how would we do that one?
Uh-huh. I know.
Magic numbers, right? That's just a quadratic trinomial, isn't it? Right? So we could just use magic numbers here. Agreed? I could use the magic numbers -9 and +2, right? Right?
And what if you can't?
Okay, well, we can though. It fits that form. But what must the u be? In order for us to get from here down to there, what would u have to be? X squared, right? Everybody see that? So I've got, if I think of this as being x squared squared minus 7 times x squared minus 18, yeah, it works, right? So the way I would say this in math is, this expression up here is a quadratic trinomial in x squared. In other words, like that, we say in x squared in math, but really what we imply by that is in pieces of x squared, or in packets of x squared, this is just a quadratic trinomial, right? And so it follows all those same patterns. Now this is what we call in math, going from x's to u's is called a variable substitution, and that's okay to do. But what did it really accomplish? All it really does is it allows us to see the pattern more cleanly, but it doesn't really change what the function is, right? So either you can do it this way, you can turn those into u's if you want to, but I would argue maybe, especially for you guys, you don't probably need to do that. You could probably just instead group the x squareds, put them in parentheses, and think of them as being like packets or quantities, right, in math would say, okay? So then it must factor the very same way, right? So we're going to get x squared minus 9 times x squared plus 2, and now we're set, right? By the zero product property, that's pretty easy, right? We can probably just jump right to the solutions. What are if I set this equal to 0, what are the solutions going to be?
3.
Plus or minus 3, right? And if I set this one equal to 0,
Something like
I get x squared equals -2, so x equals plus or minus radical 2 times I outside, right? So we get those 4 solutions. Make sense?
That's what you do with the number.
Okay. So let's look at the graph of that. Will you tell me, how many x-intercepts should that have?
3. 4.
No, not 4. See if we can come to some consensus as a group. See if you guys can agree on this. Well, how many x-intercepts should it have, and why? Think about what corresponds. It's got 4 zeros, 4 complex zeros, right? But so zeros, remember, zeros are just all of the complex numbers, could be real, could be complex, that when plugged into the function give me 0, right? So those 4 numbers that we came up with, plus or minus 3 and plus or minus radical 2i, those are the 4 zeros of this function here, right? When I plug those values in for x, in this, actually right here, right, this function, when I plug those values in for x, I get 0 for my function. You get that?
Yes.
Okay. But which of those complex zeros actually correspond to x-intercepts.
The real ones.
The real ones, right? Only the real zeros correspond to x-intercepts. Okay? So let's, for you guys, I think it might be worth just getting our vocabulary precisely correct here. Right? When we say the word zero, what does that mean? We talk about the zero of a function, right? So we would say that these numbers are zeros because, like, let's just, in general, we'll say C is a zero of a function if f of c equals 0, right? That makes sense? That's what we mean by a zero of a function. Okay, in math, here's a word that you might have heard, but we haven't really used very much yet. Different word. We would say that roots, that these numbers down here are zeros of this function, but they are roots of this equation. What's that mean? That just means that they're values of x that make the equation true. So zeros and roots mean like 99.9% the same thing. But in math, just so you guys sound smart when you go to college, you don't sound like a buffoon when you're talking to your college math professor. You talk about the root of an equation, whereas you talk about the zero of a function. And even like math majors get that backwards sometimes. But that's, technically speaking, that's really what it means. So you better get that down, T-count. Okay. What am I at right now, by the way?
Like 36.
36?
You get a work day for every
It's
time.
so
too?
hot.
No. You do not.
For every 36.
You do not. So once again, roots are solutions of equations. Zeros are values of a function, or values of a variable that make a function zero. And x-intercepts are simply the real zeros, right?
Each time it's a prime number, we get a prime interval.
Each time it's a prime number.
Yeah.
Well, the prime numbers are going to start to come pretty fast now. So,
Can we not do those?
okay, so all right, let's move on.
Uncover that box, man.
So then, if we look at this, the box. What was the box? The box, I think, was just. You got no though, don't you? I think. Oh, what happened?
What do we got going on here?
I have no idea.
Grab the box.
It's just a small version of the graph. So here's the graph, right?
It looks like a tube.
So it's got yeah. So it's got two real zeros, right? Correspond to the x-intercepts, and it's got those two other ones. What do you suppose those do? They just provide, it's, in this case, they didn't actually cross the x-intercept, but they caused the function to turn again, right? Here's another one. I'll kind of let the cat out of the bag here a little bit too. We weren't going to talk about this yet, but if this is a fourth degree polynomial, what do you think the maximum number of turning points is? Meaning peaks or valleys, minimum or maximum? 3. You guys have learned that before? You just kind of inferred that. It's 3, right. So here's one that has all 3, right? So really what those other complex roots, all they did was, in a complicated way, they just made the function turn its full 3 times. Not every quartic function that's a fourth degree polynomial is going to turn all 3 times, but it could turn up to 3 times. Okay? All right. Okay, moving on. That guy.
Yeah, we do the same thing.
Okay, we do the same thing, only what?
Twice.
Here be packets of x cubed. Right. So first of all, we'll put it into standard form. You're getting the hang of this. So we add 8 to both sides.
I don't like the word packets.
What's a better? You come up with a better one then. Huh? Groups. Okay. Okay, so we're gonna think of this in terms of groups of groups of x cubed, right? So we got x cubed squared minus 7 times x cubed minus 8 equals 0. So now we see we've got a quadratic pattern. Everybody get that? We got a quadratic pattern in groups of x cubed. Quadratic pattern in x cubed. So what are my magic numbers going to be? Negative 8 and 1. So then we're going to get whatever's being squared minus 8 times whatever's being squared plus 1. And what's being squared is an x cubed. Right?
Isn't that a difference of cubes?
It's a difference of cubes and a sum of cubes. Okay, now this time though, there's one important difference. In the last example we looked at, when right after we got this thing down to a difference of squares and a sum of squares, we can just solve those directly, right? And get all of our solutions. This time we don't have that luxury. This time we can't bail off the factoring train yet, right? Because if we do, if we set these equal to 0 and solve by cube rooting both sides, we're only getting the real solutions back, right? We have to keep going. These aren't quadratic yet, so we have to use our difference of cubes and sum of cubes patterns. Okay, so what do these break down into then? This is a difference of what cubes? The 8 is really a what cubed? 2 cubed. So the 8 we're thinking of as a 2 cubed, and the 1 is just a 1 cubed, right? So then what is this guy going to break up into using my difference of cubes pattern?
X cubed plus or minus
Well, it's a difference of cubes, right? So you tell me what comes first.
plus.
No, minus, right? It's the same. If this is x cubed minus 2 cubed, then this is x minus 2 times
X
squared
squared.
Oh, we're doing that one.
Yeah.
Plus
plus
8
8x
2x, right? AB plus
4.
2 squared.
Nah.
Yeah, good. Okay, and then this one over here, this one is a sum of cubes. So that one's, and it's x cubed plus 1 cubed, so what do we get? Good.
Oh, yeah,
Minus 1x, which is just x, plus 1 squared, which is 1. Good, and that whole thing is equal to 0, okay? So how many real zeros do we get?
6.
No, come on now, everyone should give me the same answer on this. How many real zeros do we get? 2. 2, and the 2 real zeros just come from those 2 factors, right? Remember what we talked about? Maybe you don't. I mean, there's a lot of stuff yesterday. But the quadratic part of the difference and sum of cube patterns is always going to be an imaginary solution, right? It's never going to give you back anything other than i's, right? It's going to give you back complex conjugates every time, right? Always. So if we set these equal to 0 and solve, well, this one's pretty obvious. X equals 2. Should I try to factor that one? No, never going to work. It's always going to be an irreducible quadratic, so you always have to go with some other method, right? Like quadratic formula, okay? Or complete the square or whatever. But if we set that equal to 0, I mean, we really could complete the square pretty easily on that,
Yeah, you could.
right? In fact, let's just do that.
That's exactly.
What do you? I mean, I think it's faster to complete the square if you have an even, if b is even.
Yeah.
Personally, I mean, you can decide. But.
5.
So what are we going to add to both sides? 1, right? So we're going to get x plus 1 squared equals.
-3.
So what are my 2 solutions going to be then? I'm going to have to square root both sides, right?
Yeah.
So I'm going to get my plus or minus 3, square root of 3, I, right?
Yeah.
And then what's going to go in there? Right? Everybody get it? Okay. So there's 2 more. Over here, I'm going to get x equals, okay? And then here we'll do this. Now this one, do we want to complete the square? I'd say probably not, because that's odd, right? I would, okay? So on this one, if we set that whole thing equal to 0 when we use the quadratic formula, we're just gonna get negative b plus or minus the square root of b squared minus 4ac, all divided by 2a, right? So if I simplify that, what am I getting? 1/2 plus or minus
You pretty much just solve that here, or
Yep, exactly. And zero product property, right? Look what we've managed to do. I mean, this is, we took this 6-degree polynomial equation and we broke that apart into a product of these 4 factors. And so by the zero product property, we can just find the zeros of each of those factors, set them equal to 0 and solve. Yes, ma'am?
Is there always a pattern between the two complex ones? Because it's -1 plus or minus. where-
Oh, you mean, is there a pattern between these solutions and these
Yeah.
solutions? No, not at all. Just coincidence, yeah. Okay, make sense? Okay, so we'd have to put in 6 answers on this one, remove any order. Questions? Okay, I'll let you work. Go.